Yeah.
Hello. Have you maximized? No. Probably good. I have. I don't even want to show it really. Yeah, so you maximize, you get 130. But it's not all integer, so you keep adding new constraints, keep adding new constraints, and new constraints, and you keep adding new constraints. And I think I got a bit unlucky because I was adding the wrong constraints, but you never know. And then this is the that solves it. Any questions about adding new constraints? If you're interested, I'm selling this in an auction. I'll put it on eBay. So there's no room. What we're going to do today, however, is different. Has everybody got a copy of the handout? Yeah? No, that's not what I want. Do you remember this? This is last year in November 2015.
Really? Yeah.
I think he did the same thing last year, so about 2 years ago, 2016. And that's where you were doing decision maps, and that's when you were doing this this problem. Does it sound familiar? No? Yes. Yeah. And then there was a problem. So the question is, you've got some students and you want to assign them employers or something, and it doesn't really matter too much. What it led to is you've got this in the handout, so you can read later, but I'll just briefly go through it. It leads to this graph. Okay, it's called a bipartite graph. The bipartite graph is a graph where the vertices of the nodes are in two subsets, and every edge goes across from one of the subsets. We've got these blue ones and red ones, if you like. And every edge there is in this graph is between a blue vertex and a red one. Okay, it's called bipartite. What you're trying to find is a subset of the edges such that you'd have at most one going from each blue vertex and at most one going from each red vertex. It's a problem which is exactly the same in a different guise as the problem of Alice, Becky, and whoever getting married that we started this year with. Okay? Except here you have students choosing projects, so it's a bit more boring. And in fact, the essence of the problem is, well, some allowed, it's not exactly the same problem because here you have zeros and ones as weights only, practically. Okay, so what we had was different compatibilities between girls and the boys in the problem, and here the compatibilities you can think of just there's an edge, so 1, no edge, there's a 0. So you're trying to maximize the number of edges you could compare. But no student can be assigned more than one of the project or employers, and your project can be assigned on one of the students. So that's the question. Is the question clear? No. Someone doing the type tabling punished me for something by giving me an afternoon lesson where everybody's asleep. Maybe I can evade that person. Okay, so this is how Philip solves it using maximum flows. Does that ring a bell? Yeah. If it doesn't matter because we're going to do something else. We're going to do what we did before, and that is integer programming. So it's basically a revision of this integer thing. So integer programming. That's a double L. The letter that looks like two M's is a double L. It's in line with calling the letter that looks like two V's W. If a letter that is two V's that is called W, then the letter that looks like two M's must be called double L. I think that's a pattern. Okay, so so the decision variables, you remember what they were in the marriage problem? Do you? No. Anyone? Do you remember the variables? Oh, he's not even listening.
Sorry.
It's all right. You don't have to remember the variables. Nobody else does.
We have to get a.
Probably, but I don't know where the spare ones are. Just sign him in. Okay. So these are the decision variables we had was there was one for each pair, girl and boy, right? And so here we'll have x uv for each edge. So if uv form an edge, two vertices, then you put then you introduce a decision variable for this particular edge, and then in the optimal, well, in the solution, in a solution, xuv equal 1 means that this edge is in the matching. So matching is what we're looking for, the matching. Okay, so matching is, again, you select some of the edges in a way so that no blue vertex would have two edges adjacent incident with it in that subset. No red vertex would have two of those edges. Okay, so that's called the matching, and we're looking for the one which has as many edges as possible. So a largest possible one, which is called a maximum matching, and we're doing it by having this binary variable which will indicate whether for each edge of the graph whether it's in the matching or not in the final solution. Okay, so as I said, we're looking for the largest one. So the objective is to maximize the number of edges, and of course the number of edges is you can just add all the UV over all the edges. Okay, so if you take all the decision variables that we've created and add them all together, then the number of ones among them is the number of edges in the matching, and so that's our objective. Okay? Make sense? And then the constraints were what I said. So for every vertex, no matter whether blue or red, for each of them, you want that the sum of all the x's for all these edges not be more than 1, because we only want to pick most one of these edges. Okay? So for every vertex, we can write that the sum of all the x EUVs is no more than 1. Well, what's the sum? We'll look at all the neighbors of V, and we sum all the edges. Okay? And that's that. And then we want that for all the whenever you have an edge, you want this variable to be binary. So all the variables are binary. So that's very similar to the Golden Boy problem. Okay? Do you agree? Do you like this formulation? Is it nice? Are you happy? Okay. And the reason we're looking at this is because this is a kind of a special thing. Well, so okay. So how would you solve problems? Okay. So the way you solve problems like that is you solve the LP relaxation. Okay. Well, you can't see it, but that's the idea. You don't have to see the detail. Okay. You solve the first LP relaxation, and then you add a constraint to cut it off, and then you add a constraint, and you keep cutting away, and then in the end you get an integer solution, and you've gone through a lot of simplex. Okay. Or you do a branch and bound, and that's a lot of simplex. So in general, it's quite hard to solve these problems. Integer linear problems. You never know which constraint to add, because you have several options, and when you're branching, you don't know which branch is the more promising one before you've solved it, so on and so on. Well, in some situations, in some cases, you can actually do much better. Well, you actually will necessarily do much better. And this is one of the cases. And I'll show you why. Well, I'll show you a bit of why. And that brings the definition. Okay. So that's a lot of text. Get a matrix. when you look at the matrix, you get any matrix, and then you take a square submatrix. So you select some columns and you select some rows, and you take the determinant of that. And you always get a +1 or a -1 or a 0. Imagine a matrix like that. So when you have a matrix like that, then this matrix is called totally unimodular. Don't ask me why totally unimodular, but it's called that. Are you all right with the definition? So don't know what it means. Of course, nobody knows what it means. But, the first time you see a definition like that, you have no idea. But for example, what does it mean for the entries in the matrix? So, for example, can there anywhere be 8 in the matrix? Like the number 8. In the top left corner, for example, could there be an 8? No, why not?
You can just take that as a submatrix.
Exactly, because if you just take one row and one column as a submatrix, it's a square submatrix because you have as many rows as you have columns. And it just gives you the one entry, and the determinant of that matrix is equal to the number that you found there, and it has to be 1 or -1 or 0. So this is definitely true of every totally unimodular matrix. It only has 1s and -1s and 0s. Sorry. Now, there are some special conditions as well. So these are not true in any. So what does it mean to be a sufficient condition? It means that if. What are you doing? Sufficient condition. What does it mean to be a sufficient condition? A sufficient condition means that if a matrix satisfies all this, all these conditions, then it is totally unimodular. Okay, but there are other matrices that are also totally unimodular and don't satisfy this. But if you find a matrix that has all these properties, then you can prove that it's totally unimodular. And I'm not going to prove it. But rely on linear algebra that proves it. But what's the point of totally unimodular matrices? It's the next theorem. So when you write your linear program as with matrices, okay, that's the thing that we were doing in the first term a lot. So if you write it like this, and the constraint matrix, there is things where the constraints are. So they form a totally unimodular matrix, and no matter what right-hand side you pick, as long as it's integers, you will always get an integer optimal solution. Okay. That's kind of neat. So that means that once you've solved, so if you have a problem like this with a totally unimodular matrix, and if you solve the first relaxation, it's going to give you an integer solution, and you don't have to do anything else. No branching, no adding, cutting, playing. It's just always there. That's the idea. And so I think there are kind of two things that we should look at. The first thing is we should check that, because I'm claiming that this has something to do with the maximum matching problem, but you don't have to trust me. So the right thing to, so the first thing to do is kind of check that if you write all the constraints that we had for the maximum matching problem as in the matrix form, which keeps disappearing, then we actually do get a totally unimodular. The second thing that we want to look at is, well, just kind of a hint of why this theorem is true, not a complete proof. But, okay, so these are the two things that that we still need to look at, because it's yeah, no, it's fine, it's not nice. Okay, so the first thing. No, I'm going back. So, oops. What am I doing? Sorry. So look at these constraints again. Get this constraint. We have as many constraints as there are vertices. Each of them forms a row in the matrix A. So what's the matrix? What does the matrix A actually look like? It's so each of these rows is a vertex U, vertex V, and so on. Every vertex. Okay, I'll write it on the other side. That's better. U, V, and so on. One row for each vertex. A vertex is a node. It's the same thing. In case Philip used the word node. And so for every constraint in the matrix, there's a row. For every decision variable in the matrix, there's a column. And what are the decision variables? There's one for each edge. So every edge gets a column. So one column for each edge. Okay, but you look at this. What happens is so look at the coefficients of all the decision variables in any constraint. There are lots of zeros and a couple of ones, right? Because there are a few of these decision variables come in the sum, and the remaining ones you will have to multiply them by 0. So, so every row has zeros and ones only. That's already promising. And where are the ones? Well, the ones are exactly for each vertex, for it's in the columns of those edges that the vertex is one end row. Okay, so if you're looking at so if A was the first row, then those three edges that are going out of A, they would get a 1. And the rest would get a 0. Okay, so each row looks like this. So there's a 0, 0, and there's a 1 where the vertex is, and 1 and 0. Okay, you agree? And so you get lots and lots of rows like this. But what is crucial is when you look at any one of the columns, how many ones are there going to be in the column? One, two, so 1 or 2.
Well, each just going to have 2 vertexes because there's 1. So if you've got 1 row for each vertex, then there's going to be 2.
Yeah, so that's exactly right. So they're going to be exactly 2 ones in each of the columns. 1 for the starting vertex and 1 for the end vertex. Okay. Now, there's actually more than that. In fact, because the graph is bipartite and we've got blue and red vertices, we can actually put in the matrix, we can put all the blue vertices up here and all the red vertices down there. And because every edge is going from blue to red, it's going to be exactly one for a blue vertex and exactly one for a red vertex. Okay. So we'll have one up there and another one somewhere there, and the rest of the entries are all zeros. Okay. So now let's look again at these sufficient conditions. Are they satisfied? All right. So, for example, is each thing in the matrix a 1, a -1, or a 0? Yes. There are no -1s, so only 1s and 0s, so that's fine. Doesn't say that they have to be -1. Does each column have no more than 2 non-zero entries? Exactly 2 ones and the rest is zeros. Can we split the rows into 2 parts so that in each part the sum of so in each column, sum in one part is the same as the sum in the other part? Yes, that's exactly what we've just done, because here I've split the rows into the blue vertex rows and the red vertex rows. And the sum here is 1, and the sum there is always 1 for every column. So the sum is always the same. That's also satisfying. So that matrix from Another example is totally unimodular. Okay, so but what we're actually looking at is a bit more than that. So I'll write it in a different way. So we have, I don't know why I'm doing it on the iPad. It's quite hard to write anything in there. So here we have all the x's, xuv's. Okay, that should be less than or equal to, and the right-hand sides were all ones. But we had more constraints than just those constraints for one vertex, right? We also had the constraint that every variable is a 0, 1 variable. Which, if you remember, we translated it into each of the x's being between 0 and 1. So we still should add the constraints that tell us that each of these variables is less than or equal to 1, which will make it then binary. So we've got one bunch of constraints that are expressed by that matrix A, and then we have another bunch of constraints where we need to write the identity matrix. And we have to add some ones. Into the right-hand side. Does that make sense? So this bunch of constraints are the ones for the vertices, and then for each of the edges, we have a constraint that the decision variable is no more than 1, which makes it binary. Okay. That's all. Now, we know that this matrix is totally unimodular. We want this big one to be totally unimodular. Is it also totally unimodular? No, it's totally unimodular. Why not? Anybody know? Yeah, who guesses that it's totally unimodular? Because otherwise I wouldn't be told. It is. So the thing is, go back to the definition. You know that every square submatrix of this bit here has determinant plus 1 minus 1 or 0. You want to know that in the whole bit matrix, every square submatrix has determinant value. Every square submatrix has 0, 1, or minus 1. So how do you calculate the determinant? Well, if this row, which has 1, 1, and all the rest are zeros in it, okay, this row is 1 and lots of zeros, and there's zeros everywhere else. That's the identity matrix. So Did you learn to do determinants at least a little bit about last year? You get a matrix where one row is just one and the rest is zeros, and the determinant is equal to, you just look at the rest of it. Okay? Remove this column and that row. Or maybe times -1 depending on which row it is. The odd numbered row or even. Okay? Does that sound familiar? So the same trick you do, so if your square submatrix contains some of these rows, then that just changes the sign, and when you get rid of them, the rest is totally because it is. The whole matrix is also totally easy. Okay. Now we could go on and on and on, and there are a couple of other problems that are totally unimodular, and so on. So that's quite nice. Well, I like it. Why is this theorem true? So, okay, so after the LP is solved, you know what the optimal basis is. Okay, we don't know, but no matter what the optimal basis is, what are the values of in the val column, as it were, in the simplex tableau? Well, that's key to know because they're exactly the values of the variables in the optimal solution. Right? So the values in the values of the decision variables in the optimal solution it's something you will have to know. So it was this MB inverse matrix, wasn't it? That was in the slack variable columns of the tableau, multiplied by the original right-hand side. That should look familiar. How can you calculate the inverse matrix of n? Stephen's on the trying to hurry. Okay. Well, it starts by taking the determinant and doing 1 over the determinant. Do you remember that? Times some rubbish. So this determinant is 1 or minus 1. Because it's kind of a square submatrix of something coming from A and maybe the identity on top of that. But definitely this is a 1 or minus 1. So if you do 1 over this, you get the 1 or a minus 1. This is the, what's it called? The, how do you get that? The determinant as well. If you go there,
If you just take the equal off.
yeah. So again, you only get integer numbers there. So this is a 1 or a minus 1. This only has integer numbers in it. So this only has integer numbers in it as well. So because of total unimodularity, this MB inverse only has integers in it. So if B is also all integers, the solution, when you multiply them, is also integer. That's just the idea of the proof. It comes from things that we were doing in linear programming, because this is something we got from analyzing the simplex tableau. But this is all integer. You should know from linear algebra. You put it all together. I'm leaving out all the details, but you fill in those in time. And I think there is a homework that is asking the question whether you do shortest paths, whether you also get a total unimodular matrix. Any questions? One question. Okay, so no questions. I'll see you all on Thursday.